Well, good morning. We're going to work on sections 1, 9, and 10. So if you would, take a few minutes, pause the video, and work on your warm-up, then come back and check it. So in our warm-up, we want to find the zeros of this rational function and state the end behavior using a limit. So I think to find my zeros, the first thing I'm going to do is go ahead and factor this rational function. Looks like my numerator is going to factor easily into x minus 7 and x plus 1. My denominator, however, does not factor, so I'm just going to leave it just like it is for a second. Remember, zeros of our function come from the numerator, So my zeros would be positive 7 and negative 1. Now, it does ask me to address the end behavior using a limit. And so if we're going to talk about the end behavior, I can really kind of go back and think about all those rules we talked about yesterday or the day before in terms of what's going on between my numerator and my denominator. Well, if I look, the highest degree term of my numerator is x squared. The highest degree of my denominator is x squared. So since they match, we do the ratio of their leading coefficients. And so we know that means that I'm going to have a horizontal asymptote at y equals 1. And so if we think about the limit, so if we take the limit as x approaches positive or negative infinity, we're going to get the same thing here. So I'm going to use one limit there of f of x is going to equal positive 1 because we have a horizontal asymptote there. Okay, so just a little bit of review. So now let's talk about our learning targets for today. So today we're going to talk about vertical asymptotes of rational functions and how do we find holes in the graph of a rational function. Yep, that is a thing where you just kind of have a hole in the middle of your graph. So let's talk a minute about the differences between vertical asymptotes and holes. I think it's easier to address the hole first. The hole is going to occur where factors repeat in the numerator and denominator. So if I factor the numerator and I factor the denominator, if I have matching factors there, then I am going to have a hole at that x value, okay? When we talk about a vertical asymptote, again, it's a vertical line. It's places where the function's undefined, so to speak. But basically, the easiest way to find it are factors of the denominator that do not reduce with factors of the numerator. Vertical asymptotes will always be in the form x equals a number. We'll call that number a. So anytime you're asked for an asymptote, it is a linear equation. You want to be sure that you write it in that form, x equals a. So I want to take a look at a couple of equations and see if we can find holes, if we can find asymptotes and all those kinds of things. So I like to start with a hole first just because it's easier to do that way. And if I look at this first function, do we have a factor that repeats from the numerator to the denominator? Sure, the factor that repeats is x equals 1. So we would say that we have a hole where x is equal to, it would be the 0 of that factor, which would be 1, so the opposite. So if we were to take out the hole right there, do I have any more factors in our denominator that do not reduce? And we don't, so we would have no horizontal asymptotes in this function. Okay, so no horizontal asymptotes. Let's look at the one over on the other side. Do we have any holes? Do we have any factors that repeat in the numerator and the denominator? The answer is no. Okay, so we do not. Do we have any factors in the denominator that do not occur in the numerator? And the answer is yes, we have one of those. So we are going to have a horizontal asymptote at x equals the 0 of that factor, which would be 1. Okay, so holes, repeated factors, horizontal asymptotes, denominator factors that do not reduce away. So let's look at two more together. Okay, things get a little bit interesting when we have multiplicity. So we have to think for just a second about what this is really saying about our function. And so if we look at this first one, g of x equals x minus 1 to the third over 2 times x minus 1 to the second. Well, it's pretty obvious that we've got some repeated factors. And just for the sake of investigation, I'm going to actually write that out. That's not something you're going to have to do every time, because I think you're eventually going to get to where you can see it. Okay, so let's take a look at what we've got right here. Do we have repeated factors in the numerator and the denominator? Yes, we have 2 repeated factors of x minus 1. That means we're going to have a whole at x equal to positive 1. So we have a whole. Do we have any factors in the numerator that are not in the denominator that are not simplified? We do not. Okay, so we don't have a vertical or horizontal asymptote. Nope, I'm talking about I'm talking about vertical asymptotes today. I'm tired. Oh, goodness, I had horizontal asymptotes on the brain. These are all vertical asymptotes. I promise your teacher's not a complete idiot most days. Okay, so let's go back here. Vertical asymptotes. Here we go. We got none of those. All right, maybe I can get this last one correct. Okay, so again, we've got some repeated factors. And again, just for the sake of investigation, I am going to write everything out. Okay, so my numerator x minus 1 and x plus 2, my denominator x minus 1 and x minus 1. Now, this one a little bit tricky. If we look, we do have a repeated factor here of x minus 1. So we would think, oh, I have a whole at x equals 1. But we also have this extra factor left over that's in the denominator. Well, we can't have a whole where something is undefined. So we're going to say that the vertical asymptote takes precedence over the whole. So because I'm going to have a vertical asymptote right there, we will ignore the whole. Okay, so we're going to ignore the whole. Okay, because you can't be both a whole and an asymptote. So asymptotes take precedence. So that one's going to be a vertical asymptote. All right. Well, now let's take a look at some things graphically. That's all algebraic, okay, thinking about the definition for a vertical asymptote. All right, we have factors that don't reduce that end up in the denominator, and then a whole, we have a repeated factor in the numerator and denominator. Okay, so flip that over to the next page, and let's look at this graphic for a second. Okay, so let's take a look right here. All right, so we've got 2 graphs here, and we want to find holes and we want to find vertical and horizontal asymptotes, okay? There's a lot of stuff going on in these pictures. So let's just list them. We're going to look for a hole. We're going to look for vertical asymptotes and horizontal asymptotes, okay? Do you see a hole in the graph? And it literally is what it says it is. It's an actual hole in the picture. And so if we look really closely, yep, I've got one right there. What x value does that hole correspond with? Well, it corresponds with when x is equal to 1. So we'd say a hole at x equals 1. Here in just a minute, we're going to figure out how to find that y value. This one's pretty straightforward. We could put the whole ordered pair, 1, 3, because it's very obvious where it's at. Okay, vertical asymptotes are what they say they are. They are vertical lines, and usually they're represented with a dotted line. And so if I look at this graph that we have here, we have a definite vertical dotted line that crosses the x-axis at -1. Likewise, we look for horizontal asymptotes the same way. And if we look, we do indeed have a horizontal line here at y equals +2. So we have our vertical and our horizontal asymptotes. Take a second and see if you can repeat that for the second graph. Pause the video and then replay and go ahead and take a look at what we've got there. So when we look at this one, I don't see any open circles anywhere on my graph. So we're going to say, hey, there are no holes on this one. Vertical asymptotes and horizontal asymptotes, I'm seeing those dotted lines. So I know I can see the vertical asymptote here at x equals 1 and the horizontal asymptote here at y equals 1. So we had both of those, okay? So now what I want to do today is talk about behavior around asymptotes and specifically vertical asymptotes, okay? If we look back up at the graphs that we have up here, if you notice, as we get closer to that asymptote from the left-hand side, what's my picture doing? Is it going up or going down? Yeah, it's going down. It's getting closer to that asymptote. It's approaching negative infinity. If I look at it on the other side of the asymptote, okay, so as my x values approach that asymptote from the positive side or from the right, then we notice that our graph is going up. So it's approaching positive infinity. And so when we want to describe behavior around asymptotes, we use limits. Okay, so we're going to use a limit. And this is what we're going to say. Okay, the limit as x approaches a, and we'll put a little minus sign there. Okay, so whatever we think our vertical asymptote is, whatever that number is, we'll call it a, of f of x, it's either going to approach positive or negative infinity. So if I come at it from the left, which way does my graph point, up or down? Likewise, the limit as x approaches a from the right. In other words, if I come towards the asymptote on the right-hand side of my function, what's it getting close to? Positive or negative infinity, okay? So we can describe behavior around a vertical asymptote using a limit. Well, what do we do if we don't have a graph? Because that's going to happen sometimes too. And so we're going to use, I like to call it a sign chart, to test the values near that vertical asymptote. And I'm talking really near, like we're going to use 0.5s of things, okay? But factored form is really going to help us to see that, okay? So I want to show you a couple here in just a second that we're going to talk about, okay? Can we describe the behavior around any asymptotes using our limits? And we're going to talk about just vertical asymptotes today, okay? Describing that behavior. But jump down here with me for just a second. Well, actually, you know what? Let me give you the limit statement for this second graph up here. I changed my mind. All right, let's go up here and let's write limit statements around this asymptote, okay? So we've got to do two. We've got to do the limit as x approaches something and the limit as x approaches something. What did we say we thought our vertical asymptote was looking at the graph? Yeah, it's 1. So we have from the left, 1 from the right. We're going to just call our function f of x. Okay. And now we want to talk about what's it doing on the left and the right-hand side of that asymptote. So on the left-hand side of my vertical asymptote, I'm pointing down, so we call it negative infinity. On the right-hand side of my asymptote, as I get super close to it, I am going up, so we call it positive infinity. Okay, so just to give you an idea of what those limit statements look like when we're looking at a graph. Okay. All right, so let's kind of put all of that together. So I want to look at this one. It says it wants me to determine the x values of any holes and the equations of any vertical asymptotes. So that's all it wants me to do, to find holes and vertical asymptotes. So underneath each one, this is what I'm going to write. Hole, vertical asymptote. Hole, vertical asymptote. Right? So if you think you've got it, take a second and see if you can figure these out. Pause the video, go back and look. When I look at this first one, I have a repeated factor here of x plus 3. So that means we're going to have a whole there at x equals negative 3. And then if I look at any leftover factors in the denominator, I have 1. So we're going to call that x equals 5 for my vertical asymptote. Right? When I look at the next one, and I really like this one, all right, we got to think for just a second, all right? If I have repeated factors here, I have 1x plus 1 on the top and 2x plus 1s on the bottom. If I reduce those, where am I going to be left with an x plus 1? Yep, it's going to be on the bottom. I have 1 here and 1 on the top, 2 on the bottom. So this is just going to leave me with 1x plus 1 on the bottom. Okay, so that's a factor on the bottom. Then we look at our x minus 2s. I have 2 on the top and 1 on the bottom, which means I'll just have 1 left on the top. Anything that you have left on the top means that's a whole. Okay, so I'm going to have a whole at x equals positive 2. And then anything left on the bottom is going to be my vertical asymptote, which is going to be x equals negative 1. So a little bit tricky on that one. You got to think about how many you've got. For some of you, it might be better if you just physically write out how many terms you have of each one so that you can see where you have things left over. All right. Now, C looks really good, except the only problem is it's not in factored form, and I really should do that. If I factor on the bottom, I could pull out an x, and that would leave me x squared plus 4. Okay, if I pull out an x, it would leave me x squared plus 4. So if we think about a whole, do we have anything that's going to factor that's going to match in the numerator and the denominator? We're not, so we're not going to have a whole. Now, vertical asymptote on this one's a little bit tricky, okay? Because if I take, I'm going to actually think about the possibility of having 2 because I've got 2 factors down here. Well, I know x would give me just x equals 0. But I want you to think for a second about x squared plus 4. If you were to set x squared plus 4 equal to 0 and solve for x, what would happen? Yeah, you're going to get an imaginary number, all right? Asymptotes cannot be imaginary, all right? So the only asymptote we have is at x equals 0, all right? It's the only one we have. Okay, so think about that one. You can't have imaginary numbers for asymptotes. All right, now let's look down here at example 2. This is a good example. This is where we don't have a picture and we want to use those limit statements to describe the behavior. And so if we're going to use a limit statement to describe the behavior, and we're going to talk about vertical asymptotes here using limits, the first thing we've got to do is to identify where is our asymptote, okay? So if I look right here, I've got a vertical asymptote at x equals positive 2. So my limit statements have to say this: the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Okay, so it's either going to be positive infinity or negative infinity. Well, how do we tell? So let me show you this organizational tool. All right, I call this a sign chart, and on my sign chart, I put my vertical asymptote. All right, what I want to do is I want to choose a value that is close to positive 2. All right, a little bit above it, a little bit below it. Okay, so I'm going to think about using 1.5 and 2.5. Okay. Now, the next thing I'm going to do is I'm going to kind of just do signs here. If it's positive infinity. If it's negative infinity. So what I'm going to think is if I take 1.5 and I plug it in for x in every one of those parentheses, okay, what sign do I get, positive or negative? So 1.5 minus 1 would be a positive. 1.5 plus 3 would be a positive. 1.5 minus 2 would be a negative. What happens when I get 2 positives on the top and a negative on the bottom if I reduce it? Would I get a positive or a negative? Yes, that would give me a negative. So on the left-hand side, we are approaching negative infinity. All right, we're just talking about the values of the numbers. Now, let's choose 2.5. Let's repeat that process. Let's take 2.5 and plug it in for every parenthesis and look at our signs, okay? 2.5 minus 1 would be a positive. 2.5 plus 3 would be a positive. 2.5 minus 2 would be a positive. Well, what happens when I get two positives over a positive? You betcha it's still positive. So on the right-hand side, we're approaching positive infinity. Now, that's a lot to take in. You might need to go back and re-listen to this portion, okay, so that you totally understand what's happening right here, okay? All right, next one. Okay, so again, here we've got some with some multiplicities, all right? And I'm going to fix that multiplicity first because I've got an x minus 2 and an x minus 2 squared, all right? This is going to leave me, all right, if I reduced with x minus 4 over x minus 2, x minus 1, all right? Now, this means I have how many vertical asymptotes? Yeah, I've got 2. I've got a vertical asymptote at x equals positive 2 and at x equals positive 1, which means I actually need 4 limit statements. I need the limit as x approaches 2 from the left of h of x, the limit as x approaches 2 from the right of h of x, okay? Then on the other one, I need the limit as x approaches 1 from the left of h of x, and the limit as x approaches 1 from the right of h of x. Okay, so we're going to need 2 sign charts, all right? All right, here we go. And we could kind of do them all at the same time, but I kind of like to do them separate just so I know I didn't miss anything. Okay. All right, so again, we want to pick numbers that are close to what we're looking at, okay? So if I choose 1.5 and 2.5, right, always plug back in to your original, okay? Not from where you simplified, but into your original. And so if I do that, all right, 1.5 minus 4, that's going to give me a negative. 1.5 minus 2, that's going to give me a negative. 1.5 minus 2, but I have to square it. Anything I square is always positive. And 1.5 minus 1 is going to be a positive. Now, tricky right here. What's a negative times a negative on the top? It's a positive. Positive divided by positive is a positive. Okay? So now let's do the same thing with 2.5. If I plug that in, 2.5 minus 4 would be a negative. 2.5 minus 2 would be a positive. 2.5 minus 2, but I'm going to square it, so it's going to be positive. 2.5 minus 1, it would be positive. So if we look at this, negative times a positive is a negative. Divided by a positive, it's going to give me a negative. Now, one of the things that I'll caution you about is not just assume aside, that's the word I like to use, that things alternate, okay? It could be that we get one where they both go towards positive infinity. That's going to happen periodically, okay? So my first one, on the left-hand side of 2, it goes to positive infinity. On the left-hand side of 2, it goes to negative infinity, all right? Let's check it around 1. We're still going to use the same function, right? But to the left of 1, I might use 0.5, and to the right of 1, I might use 1.5. Well, here's the cool thing. I've already used 1.5 in that function. And what answer did I get over here? Yeah, I got a positive, so I'm just going to put positive right there. So we could have done this all on one number line and looked at it once, okay? So that's always an option. Now, if I put 0.5 back in, let's check our signs here. 0.5 minus 4 is going to give me a negative. 0.5 minus 2 is going to give me a negative. 0.5 minus 2, it doesn't matter, that's going to be positive. And then 0.5 minus 1 is going to give me a negative. So on the top, I'm going to have a positive, because negative times a negative is a positive. And then on the bottom, positive times a negative is a negative. So when we write in our behavior, on the left side of 1 is negative infinity. On the right side of 1 is positive infinity. Okay? So that's different, okay? Check in those, check in those behaviors around those asymptotes. Plug in that number in, okay? Really, really, really important. So those sign charts should look familiar from what we did the other day, okay? All right, hopefully your brain's not too far overwhelmed, and if it is, just your way through it. It'll be okay. All right, let's look at the next page. All right, so I told you there'd be a way where we could find the y value of the whole. And the way that we do that is using a limit, okay? Because here's the problem. We can't really plug in a value where we think the whole is into the function because the function is not defined there, okay? So what we're going to do is this little process, all right? We want to get as close as we can get as possible. That's a limit. So the first thing we're going to do is factor. We're going to cancel out the whole. Actually, I hate that word cancel. Let's say reduce the whole. And then we're going to use a limit of what's left. And let me show you how that works. Okay, because we want to get as close as we can without actually plugging it into the function. That's the biggest mistake that people make is they try to plug it into the function, and we can't. We have to use a limit. So let's take a look at the one we've got right here. I've got f of x equals x squared minus x minus 6 over x plus 2. So let's factor. The numerator, nice pretty trinomial there, is going to factor into x minus 3x plus 2. Well, you should see the whole and see it pretty quickly, okay? What is the x value for your whole? Yeah, it's going to be at x equals negative 2. Well, let's reduce out the whole, and then what am I left with? I'm left with x minus 3. So here's what we're going to take. Here's what we're going to do. We're going to take the limit as x gets close to where that whole is, which is negative 2, of the function that's left. And all we have to do to evaluate that limit is plug in this x number for x. So negative 2 minus 3 equals negative 5. So the ordered pair for my whole is at negative 2, negative 5. Now, a lot of people like to say, Ms. Moore, aren't we just plugging something in? Yeah, we are, okay? But mathematically, I can't really do that without this notation of a limit. On the AP exam, they will not give you credit on a free response question without that limit. So it's really important that you get used to doing it, okay? Let's do another one together, and then I want you guys to pause the video and try one. All right, so we reduce, we write a limit statement, and then we plug in. That makes it all legal, and we'll talk more about that in calculus next year. But right now, I just need you to understand that that's how we prove that it's true and have sound mathematical doctrine, so to speak, okay? All right, so let's look at this next one together. We want to find all the wholes. We want to write a limit statement to determine the exact location of the whole. That means give me the ordered pair, okay? So if I look at g of x, it's already factored for me, which is nice. It's pretty obvious that we've got a whole right here because we've got a matching factor. So we know our whole is going to happen at x equals positive 2. If I reduce that out, it leaves my g function to x plus 4 over x minus 3. And so to get the ordered pair for my whole, we're going to use a limit statement. We're going to take the limit as x approaches that number where the whole is, which is 2, of x plus 4 over x minus 3. Well, we're just going to plug it in. Once we plug in, we can drop the limit. So 2 plus 4 over 2 minus 3 gives me 6 over negative 1 or negative 6. So my ordered pair is 2 comma negative 6 for my whole. All right, pause the video. You try the second one. All right, let's check our work. Okay, so the first thing we need to do is to factor. So this is going to factor into x plus 7, x minus 5. In the numerator, I'm going to have x minus 5 and x plus 2. So I think, again, we can see the whole. The whole's going to happen here at 5. So if I reduce that out, it leaves me with x plus 7 over x plus 2. And so if we do our limit statement, I'm looking for the limit as x approaches 5, that's where the whole is, of x plus 7 over x plus 2. And if we plug that in, that would give me 5 plus 7 over 5 plus 2, which would be 12 over is that right? 12 over 7. Sorry, I had a brain sparkle there. So my whole would occur at the ordered pair 5, comma, 12 sevenths. So sometimes it's going to be a fraction, and that's okay too. All right. Yeah, making sure I factored right there, y'all. Okay. All right. Question about that. All right, well, let's take it just one step farther. Okay, what comes next? How do we look at this type of problem? Okay, so this time it wants me to write the equation of a rational function. All right, so it's telling me some things. It's giving me some limits here. It says the limit as x approaches 3 from the left of f of x is 5. The limit as x approaches 3 from the right of f of x is 5. That means we have a whole. Okay, we have a whole, and the whole happens at the point, 3 comma 5. Okay, so we're going to have a whole at 3 comma 5, so that's important to know. Our other limit, the limit as x approaches 1 from the left and it approaches infinity, limit as x approaches 1 from the right and it approaches infinity, means that we have a vertical asymptote. Okay, at x equals 1. So let's think about what that would look like in function form. All right. For me to have a whole, then I have to have a matching factor on the numerator and the denominator. Well, that matching happens at 3. So I'd have x minus 3 on the top, x minus 3 on the bottom. All right. Likewise, I have a vertical asymptote at x equals 1, which means I'd have a factor in the denominator, which was x minus 1. Well, where does this 5 come in? Because I've got to be able that when I reduce and plug in 3 that I would get 5. Well, it comes in a factor that we like to call k right there at the top. Okay, and here's the easiest way to solve for k. If we set up that limit, okay, the limit as x approaches 3, and I reduced out, think about what would happen if I had reduced out where my whole is over x minus 1, we know it should equal 5. That's what it tells me. The limit as I approach 3 should equal 5. Well, that means I just need to plug in 3 for x. So k over 3 minus 1 is going to equal 5. Well, let's solve that equation. That means k over 2 equals 5, and so k is just 10. So my actual function f of x equals 10 times x minus 3 over x minus 3 times x minus 1. It would not be unlike the AP test to multiply all that out and give it to you not in factored form. Okay, so just a helpful tidbit right there. Okay. All right, let's take a look over here at this next one. I think this one's interesting too. All right, so same thing. We're trying to write the equation of a function. Let's see what they told me. The limit as x approaches 2 gives me a value. That means those are wholes. It's a whole, okay? The whole happens at the ordered pair, -2, 4. That's important, okay? The next thing that's important is that we're approaching at -1 from both sides. We're approaching an infinity, okay? Which means we have a vertical asymptote, all right, at x equals -1, okay? At x equals -1. Now, here's where we got to really think about what we know about a function, because when I start messing with this, okay, we know we've got a whole at -2, so I've got to have an x plus 2 on the top and an x plus 2 on the bottom. In order for me to have a vertical asymptote where they both approach infinity, think about what that would look graphically, all right? So if I have this asymptote and everything's approaching positive infinity, that means it's up on both sides. It can't be an opposite. Anytime that happens, we're going to square the asymptote. Okay, so I'm going to write x plus 1 squared. If you think about the function 1 over x squared, all right, it looks a lot like this. It turns up like that. okay? The other piece missing is that k we have to find because we got to make it all equal 4 when I take the limit and I reduce, right? So let's jump into the limit statement. If we jump into that, we would reduce the x plus 2. So I take the limit as x approaches negative 2 of k over x plus 1 squared, and it told me it had to equal 4, right? And so if it's telling me it has to equal 4, then let's plug in negative 2 for x. So k over negative 2 plus 1, we're going to square it, is equal to 4. Well, on that bottom there, I get negative 1. So k over negative 1 squared equals 4. That'd just be 1. So k is equal to 4. And so my final function, f of x, is equal to 4 times x plus 2 over x plus 2 times x plus 1 quantity squared. All right, that one's tough. All right, there's a lot to think about in that one. Okay, but any time that they're facing the same direction, we got to square it. Okay, we got to square it. All right. Okay, let's look at just a few more. We're going to be finished. Last thing we need to be able to do is to generate a graph based on the descriptions they give me. Okay, so we need to be able to generate a graph. So let's take a look at this one. A lot of times these will be multiple choice on your exam, but there is a chance that it could be on the free response. So if we take a look at this one, first of all, it tells me that f of x has a hole at x equals 1. All right, well, that's good to know. Okay, we've definitely got a hole. Then it goes on to say, as x approaches 4 from the left, f of x increases without bound. That means it goes towards positive infinity. As x approaches 4 from the right, it decreases without bound. That means it's approaching negative infinity. Y'all, this means we have a vertical asymptote at x equals 4. So let's draw that in. We have a vertical asymptote at x equals 4. It also tells me that I have a hole at x equals 1. I don't know what the y value is, but somewhere when x is 1, I've got a hole. Okay, so my function on the left-hand side is growing without bound as I get close to the asymptote. All right, I don't know what else it's doing, but I could say it might be doing that. Okay, on the opposite side of the asymptote, it tells me it's decreasing without bound. Okay, so it could be doing something like that. All right, there's no hole on that side, but that it's just decreasing. Okay, and that's a possible sketch. And let's take a look at this last one. Same thing. Oh, this time I got 2 holes. All right, so I've got holes at x equals negative 2 and at x equals 3. As x approaches negative 1 from the left, it decreases without bound, so it's going to negative infinity. As it approaches negative 1 from the right, it's also decreasing without bound, so this is a vertical asymptote. Okay, when my function goes towards infinity, it's a vertical asymptote. So let's put that in, a vertical asymptote at x equals negative 1. Okay. They're both approaching negative infinity, but I have holes here, okay? So I'm going to put the first one in at negative 2 first, and when I graph it, it might be doing something like that, all right? And then at positive 3, we're going to have a hole as well, so it could be like right there, but it's just going to get close. Right? We don't know if it's even or odd or if it makes some kind of snake shape or anything like that. We just know that on both sides of the asymptote, I got to get close to negative infinity. Okay? So a lot covered today, vertical asymptotes and holes, kind of pulling together everything we know about polynomial functions in conjunction with a fraction. Your lesson practice, you'll get that tomorrow, all right? I encourage you to go back and look through these examples if there was something you didn't know, if you want to get a head start for tomorrow so that you don't forget, and practice a few. It'll be on the assignment for tomorrow, so you can go ahead and look at it and see what you're going to need to work on in class tomorrow with each other, okay? Good luck. I'll see you guys soon.